Can we expect our measurements to be error-free? Absolutely not. We are humans, and we are using tools created by humans, imperfect tools, in the hands of imperfect engineers, surveyors, and technicians. So we need to understand the nature of our errors. Two primary types of errors I want to alert you to. You are probably familiar with these concepts already, but it's worth reviewing. Systematic errors are those that can be measured or quantified. For instance, if you are measuring the length of a football field with a yardstick, you can lay that yardstick down end to end and come up with a whole number of yards to the end. But when you get to the end, you find that, oh, the number didn't come out like I expected it to. Lo and behold, this is a meter stick. Well, the difference between a meter and a yard is a fixed value, and that is a systematic error. Given your systematic error, you could apply it to your erroneous measurement and you can come up with a corrected value. Well, not only can you quantify that error, but it has a positive or negative value. By contrast, a random error is one that is an accidental or a blunder error. We can't quantify it because all we know is it exists. It's akin to admitting to your partner that, hey, I misread the rod. Well, if your partner asks, well, how much did you misread it by? That's a silly question because, first of all, if you knew you were misreading it, you probably would have not made the mistake. But you don't have any evidence after the fact of how far you misread it. You may be able to deduce what the error is, but you cannot quantify it reliably. Now, in leveling, let's make a list of systematic errors and random errors. Systematic errors include things like earth curvature and refraction. Fortunately for the type of surveys that we are learning in this course, these errors are negligible. When the distance to your rod is less than 300 feet, this becomes a very tiny error. But when your distances start to surpass 600, 700, 800 feet, maybe even 1,000, and the intended use of your measurement requires a certain level of accuracy, you may need to include earth curvature and refraction corrections in your leveling measurements. This is most appropriate for things like trigonometric leveling. A maladjusted instrument certainly is going to be an error source, and we're going to spend a little more time talking about this at the end of this lecture. Metals expand as they heat up and contract as they cool, and we used to use leveling rods that were primarily wood rods with lightweight metal faces. Well, those metal faces didn't necessarily change shape much at the 100th level, but over their overall length, you could have a scalar effect on those, on the graduations on the rod. In these days, we typically don't use rods of that type very much anymore. We prefer to use fiberglass rods, which are more dimensionally stable over a wider range of temperatures. However, for precise leveling, very precise leveling, there are very specialized alloy rods for which we must take temperature measurements and correct for temperature-induced length changes. If your rod level, or your level rod is not plumb, then you're going to have a reading that exceeds the truth. When you are dealing with a horizontal line of sight and a vertical rod, then you will get the minimum reading between the point measured and your line of sight. But if the rod is not plumb, then your reading will increase. This type of error is a systematic error only if you know the slope of the rod. If you don't know the slope of the rod, this is merely a random error. Random errors include the instrument not being level. It either is or it isn't. and determining the degree to which something is out of level requires another instrument to do it. So that's impractical, so we're going to treat this as a random error. A bad rod reading, like I said before, if you misread it, do you know by how much? Probably not, because you didn't know you misread it until afterwards. A poor turning point. A turning point needs to be stable, sufficiently stable to maintain its position and its elevation long enough to take a foresight reading, to allow the instrument operator to move the instrument to a new location and level it, and long enough to take a new backsight in order to establish an HI at that new instrument location. Things like loose rocks on the surface do not make good turning points, but hard, massive objects and things like spikes driven to refusal in the ground do make good turning points. And we'll give you pointers on that in the field as we go this semester. Parallax is an optical error induced by the mismatch of the focal length of your eye and the focused lenses of your instrument. When those two focal lengths come into harmony, then parallax is eliminated. But when parallax does exist, that random error is wholly dependent on the position of your eye relative to the eyepiece of the instrument, and that has a random pattern. Heat waves affect your ability to see across hot surfaces. You've noticed the shimmering effect of the sun beating down on a reflective surface, and you can imagine what that does to your ability to read the rod, even at short distances. The harder it is to read the rod, the more likely you are to have a random rod reading error. Likewise, the wind can affect the rod by blowing it out of plumb. If you take a telescoping rod and run it up to 25 feet, well, it's going to be hard to keep that thing still. Likewise, the wind can affect the legs of your tripod and make them vibrate, making it difficult to read the instrument while it vibrates. Some amount of error is acceptable, and this is the basic tenet of error management. Error management is one of the things that separates surveyors from anybody else that owns that equipment. And surveyors and engineers need to understand very, very clearly that we cannot get rid of our errors, and we have to know what the acceptable level is. For instance, if you are setting construction stakes from which to build concrete curb and gutter, you know that in flat terrain we probably need to set those to the nearest eighth of an inch so that we ensure or we prevent the formation of puddles in that curb and gutter after it has secured and become hard. Well, you don't necessarily need to measure the nearest hundredth of a foot if you are establishing rough grade for the preliminary dirt work on a subdivision site. The heavy equipment can only measure or only cut to probably the nearest tenth of a foot. So some amount of error is acceptable, and that is based on the intended use of the measurement. Acceptable error is determined by the intended use of the measurement. Most construction surveys and engineering surveys require third order accuracy. We're going to talk about what that accuracy requirement is momentarily. So our aim is to equip you with good leveling procedures that are designed to minimize systematic and random errors. Can you eliminate them? No. But can you minimize them? Yes. Instrument calibration and other processes will help you minimize systematic errors. Other blunder prevention practices will help reduce the occurrence of random errors and even reduce their overall size. When we talk about accuracy, there are three primary levels of accuracy you need to understand. First order accuracy is that accuracy required for a basic framework of the National Spatial Reference System. And this accuracy is appropriate for precise control of large engineering projects and scientific studies. If I compare that to second order accuracy, first order is a higher accuracy, or another way of looking at it is those benchmarks who have first order accuracy have been measured more precisely and more accurately than second order accuracy benchmarks. Second order accuracy benchmarks are those that add to the basic framework for major engineering projects. The majority of benchmarks that you will interact with are third order accuracy, and these serve as a vertical reference for local engineering projects, topographic surveys, drainage surveys, and mapping projects. So the majority of benchmarks that you will encounter are third order benchmarks. You will then come across some that are second order accuracy, but the ones that you will encounter the least are first order accuracy benchmarks. This is the smallest percentage, the smallest fraction of benchmarks are first order. Now, if we compare these numerically, you'll see that third order is indeed has a larger allowable error than first order surveys. On the right you can see some metric to English equivalencies, and let me explain those for you. If we look at the third order accuracy standard in metric, the distance k is the circuit length in kilometers. Or in English, the distance m is the circuit length in miles. So consider a third order level circuit that is 1 mile long. Perhaps it starts and ends at the same place. So it's a loop 1 mile long. Well, if I take the square root of 1, which is 1, times 0.05 feet, then I have an allowable error of 0.05 feet in my circuit. That means my calculated elevation needs to agree with the known elevation at my closure point to within plus or minus 0.05 of a foot. You can see by the coefficients there on the remaining second and first order specifications that those are far more restrictive. To achieve first order class 1 accuracy requires a great deal more effort and not only stronger methods but higher precision equipment. Second order can be achieved with the equipment that you will see as a part of this course. If your measured closure error is less than the computed allowable error, then your circuit is acceptable. However, if your measured closure error exceeds the allowable error that you calculate based on the desired specification, then you may need to rerun all or part of the circuit. Now, when you have your completed circuit, if you have come back to your starting point, your computed elevation at the end of your circuit may not necessarily be the same, and will likely not be the same as your known elevation. Why? Well, that's the sum of your errors. Those errors have accumulated through that circuit, and they become evident when you get to the end. Well, did the errors only happen at the end? No, they happened hopefully they were somewhat evenly distributed, but even then that distribution is a bit random. So we need to adjust an error. So for every error like this, we can apply a correction. We're only going to do this when we're establishing new benchmark elevations, because these will be the reference for other subsequent surveys. Common methods that we use for adjusting our closure error, those common methods apply a linear correction to generally randomly distributed errors. So effectively, our correction has error inherent in it, but we are distributing the errors in order to keep a concentration of errors from accumulating. If you are dealing with large control networks, such as those that run across entire states or even the nation, a fairly complicated least squares adjustment is needed for those, and that goes beyond the scope of this course. We can adjust our benchmark circuit errors by distributing those errors across the number of benchmarks measured. For instance, if you have 3 benchmarks in the circuit and you have 6/100ths of error, and let's assume for our purposes that that meets the appropriate criteria, then for those 3 benchmarks you may adjust the first one by 2/100ths, the second one by 4/100ths, and the third one by 6/100ths, 6/100ths being your total. So this may be an appropriate application for some circuits. Other circuits, it may be more appropriate to distribute the error by the number of turning points. I think you can understand if you have established a turning point, you have established another instrument setup. So for every instrument setup, you have error sources. And if you have a disproportionate number of error sources between any pair of benchmarks, then that may be a place that warrants additional error to be distributed in that portion of the circuit. The method we're going to use for this over the next several days will be to distribute the error by the cumulative distance to each benchmark. Using 3-wire leveling methods, you will be able to not only improve the confidence level of each backsite and foresight, but you will be able to measure using the stadia hairs in your instrument the distance from the instrument to each backsite and foresight. The cumulative distance to each benchmark will then readily come forth from your notes and be a part of the basis for distributing your closure error appropriately. As I promised a little bit ago, I want to talk about the systematic error attributed to a maladjusted instrument. And the great thing about automatic levels as we have them today is they can be calibrated in the field, not just tested but adjusted. Certainly you can send your automatic level to an instrument supplier, a vendor who can adjust it for you, but once you know how, it makes the most economic sense to do it yourself. So the process goes like this. You need a line on relatively flat ground. You don't have to have the entire line marked out, but consider it having 3 points. And at the 2 end points, about 300 feet apart, you'll have a rod. 2 identical rods can work, or 1 rod moved back and forth from point to point. And then at the midpoint of this 300-foot line, set up your automatic level. With the instrument there, you should be midway between those points. So in my illustration, I'm showing that it's 150 feet from one rod to the instrument and 150 feet from the instrument to the other rod. If I take the readings in this condition, I say that the backsite and foresight distances are balanced. That is, they balance each other. The difference in the rod readings will give me the difference in the elevation. Now, in a perfect world, the horizontal line of sight will be represented by the black dashed line that you see there. But in reality, if your instrument is out of adjustment, then its line of sight may be sloping, as is indicated by the red dashed line. When your backsite and foresight distances are balanced, then that error induced by that sloping line of sight will be identical at one rod compared to the other rod. So the difference in the rod readings will effectively cancel out the error that occurs at both places. Now, if this is the balanced part of the test that we do first, then we're going to imbalance the back sight and foresight distances. So to do that, we'll move the level to near one end of the line so the level is at some minimum readable distance from the rod. 5 or 10 feet is going to be fine. There are ways to get it closer, but in my experience, the difference is negligible. So let's say I'm 10 feet from one rod, the same rods in the same spots. Then my inclined line of sight over 10 feet will yield a very, very small, if not negligible, error. But that same inclined line of sight, now extended over 290 feet, will give me a fairly large error. Well, if this error exists, then the elevation difference in this imbalance condition will not match the elevation difference in the balanced condition. So if they do not match, if those values are not equal, then I have an error. And that error can be adjusted in the field. Most of our instruments have adjustment screws that can be revealed by removing usually a small cover on the eyepiece of the instrument. And once that is exposed, then we can adjust the horizontal crosshair up or down to yield the more correct reading. Once you make an adjustment like this, you need to repeat the entire peg test to ensure that you have made the adjustment in the correct direction. As I was learning this years ago, I recall having applied my adjustment, and to my shock, after I checked it, discovered that instead of eliminating the error, I doubled the error. So I reran it a few times until I was confident that I had eliminated the error. But always retest when you adjust. As we wrap up this particular lecture on leveling, there are 7 basic rules that I would like to point out to you that will guide your field work and help you understand the impact of errors on what we do. Number 1, make sure that you balance the length of your foresights and back sights. This comes right out of the concept of peg tests, but certainly is used to eliminate those systematic errors due to minor maladjustments. And I'd recommend you try to keep your foresight and backside distance to about 300 feet. Beyond that, it starts to get difficult for a beginner to read the rod reliably. Number 2, make sure that the instrument is level and the pendulum swings free. Here you see it says make sure the gun is level. We use the term gun as slang for instrument. We're not talking about a weapon, we're talking about an instrument. So make sure your instrument is level, and the pendulum in the automatic compensator internal to the instrument swings freely. You'll know that if it jingles, and we can show you some other methods in the field to ensure that it works properly. Number 3, treat all benchmarks as turning points, or as we would say, turn through all benchmarks. This way, every foresight that you take on a benchmark establishes it as a turning point and thus puts that benchmark on the closure loop. It is that closure loop that the final closure error for which the final closure error indicates the quality of your work. Number 4, give complete descriptions of benchmarks and temporary benchmarks. The purpose of the description is enable a complete stranger to find your benchmark. Fortunately, I have, when surveying in strange cities, strange to me that is, in different states, I have been the beneficiary of well-written benchmark descriptions that have enabled me to find things I've never seen before that were even buried inadvertently. Number 5, in order to ensure a plumb rod reading, have your rod person rock the rod or use a rod level. Rocking the rod is going to make the rod reading from the instrument's perspective appear to bounce. Well, at the bottom of each stroke, you will find that the minimum reading occurs when the rod is plumb. Or, if that is not a method you prefer, a rod level held to the side of the rod and with its bubble kept in the bullseye circle will ensure that the rod is plumb. Make sure that your turning points are solid. They have to be solid enough to allow 2 shots and the movement of an instrument between those shots. If it can't be stable or reproducible for that long, then it's not an adequate turning point. And then number 7, ensure that you close all your level circuits on benchmarks of the same degree of accuracy. If you are doing first order leveling, it would not make sense to start from a first order benchmark whose elevation is known to a much higher quality than a third order benchmark and then turn around and end your circuit on a third order benchmark. If you start on first, you need to end on first. If you start on third, you should end on third. It is possible to start on third and end on second, but there is not much gain in doing so. So make sure that you are aware of the error inherent in your benchmark. You see, your measurements all contain error. The benchmarks you use also contain error because they were measured by humans. So in every measurement there is error. In every elevation there is error. In every position there is error. It will be very important that you view everything we do this semester with an eye toward error sources. Hopefully this discussion today has opened your eyes to the imperfect nature of what we do and things we can do to mitigate the imperfection in our work and get it closer and closer to the truth. Thanks for your time. We'll be talking to you again very soon.